Next, we move on to preparing data for machine learning. So data target is equal to data price dot shift -1. Basically, this creates like a target variable of like the next day price. Then we do data clean is equal to data dot drop NA. Basically, this removes the rows with like missing values. Afterwards, we print like the clean data shape, the data range, and like the target variable clean dot describe. Basically, the clean dataset shape is now 365 rows to 103 columns. The date ranges from 2020 02 to 19, from 2020 12 to 12 to 29. So target variable has the count, mean, standard deviation, minimum 25 percentile, 50 percentile, 75 percentile on the max, and then here we have like the data type for it, which is like a float 65. Next, we move on to feature selection. So feature columns is equal to for call, and data clean, columns if not call, and price and tag. Basically, this creates a list of like all the potential predictive variables, such as like lag variables, moving averages, and like technical indicators. Next, then we calculate the correlation matrix for the features by using correlation matrix equal data clean feature column to correlation. Then we have high correlation pairs is equal to empty brackets all the way to correlation matrix dot ilock brackets I and J. Basically, what this block of code does is it systematically finds all the feature pairs with like a correlation of like 0.95. Then we have print found length high correlation pairs, correlation of features pairs greater than 0.95, all the way to print pair equal to pair 1 equal to pair 2 dot 3f. Basically, this provides like transparency about which features are considered for removal. Then we move on to feature to remove dot set for pair and high correlation pairs, features to remove add pair 1. Basically, this block of code systematically removes like one feature from each of the highly correlation pairs. Afterwards, we do final features for call and call feature call, if not call and feature columns to remove. Final feature count is equal to length of feature, then remove length features to remove highly correlation. So here's our output. So found 317 highly correlated feature pairs above 0.95, and here like the sample high correlations. So returns and logs returns has like a high correlation all the way down to like price lag 1 to compare it to price lag 2, which has this correlation of 99.9. And the final feature count is 49, and we removed like 52 highly correlated features. Then we move on to importing a standard scalar, min-max from pre-processing, importing linear regression from linear model, random forest regressor from sklearn assemble, and mean square error, mean absolute error, and R2 score from the sklearn metrics. Then we move on to x is equal to data clean, final features, and y is equal to data clean target. Basically calculates the feature matrix of x and the target vector of y for the machine learning models. Then we do split date is equal to date clean index int length data clean times 100. Basically, this determines like the cutoff date for like the training and testing split, and we do it times like the 80% for the training. Then we have x train equal to x index less than or equal to split date all the way till y test, which is equal to y brackets y index, which is greater than split date. Basically, this block of code basically splits the date chronologically into like training and testing sets. Then we move on to printing out the training set, the testing set, and the training period, the testing period. Then we have scalar is equal to standard scalar to x train dot scaled, scaled is equal to scaled dot fit, x train x test scaled is equal to scalar dot triangle x test. Basically, this normalizes the features we have to have like a mean of 0 and standard deviation of 1, as many machine learning algorithms perform better with scale data. Afterwards, we print out the feature matrix shape and the target vector shape. So here's our output for this. So training set is equal to 253 samples, testing set is equal to 62 samples, training period is equal from 2020 to 02 19 all the way to 2020 10 to 28. Testing period is 2020 10 to 29 to 2020 12 to 29. And here's our feature matrix shape with 253 to 49. Target vector is equal to 253 rows. Next, we move on to building and training predictive models. So models is equal to linear regression with these parameters, random forest with these parameters. Basically, this initializes the models, Then we have models is equal to results per empty brackets. This is to train and like store the results. So we have a for name and model items, model dot fit x scaled and y train. Basically, this trains and evaluates the model. And then we have train predict all the way to test predict. This basically makes predictions for the model. And then afterward, we calculate the metrics of train RMSE all the way to test R squared. And afterwards, we basically store these variables in here in the model's results brackets name. And afterwards, we basically print out the training RSME, the testing RSME, and the test R squared. So here we have the data for the linear regression model for the training RSME of like 0.8893 and a test RMSE of like 1.4352 and a testing R squared of 0.8841 and and then we have the random forest classifier with its results of training RSME of 0.4432 and the testing RMSE of 4.334 and a testing R squared of negative 0.568. Basically, the linear model in this case has done a better job, and it has a very high accuracy for the training RSME of like 88.9%, and for R squared, which has an 88.4%, as compared to the random forest, which only has like 44.3% for the training RSME and having a negative 0.568% for like R squared, basically showing that the model has done a lot worse than like the linear regression model. So yeah, overall the linear regression model is like the better model as it's consistent and has like very reliable performance overall. So yeah, so here's the entire project. Thank you for listening and watching.